Good afternoon. My name is Giovanna Rapella and I'm a postdoc research fellow at the University of Calabria. So the work I'm going to show you today is about the improving of adhesion and macroscopic energy dissipation in adhesive joints used pulsed laser surface pretreatments. So here is the outline of my speech. So after a brief introduction and the objective, I will show you the objectives of the work, and I will divide the experimental work in the surface modification based on the laser, and the second part will be on the adhesive bonding procedure, and I will conclude and show you the future works. So I'll try just to be very brief on the introduction, because all of you know, of course, what is adhesive bonding, and you know that this joining technique is gaining fields all over the industries because it has advantages such as the capability to bond huge surfaces and also dissimilar material. Also, as you know, we have the possibility by adhesive bonding to have a more uniform distribution of the stress in the mating surfaces. So, of course, we can increase also the life under services of the product that we are joining together. Of course, when we want to bond two materials, we have to be sure about the surfaces that we are going to bond together. In order to do that, usually at industrial and research level, common treatments are chemical or mechanical treatments. The more commonly used, especially for metals, are chemical treatments. And that's because they are demonstrated to be effective. They don't only modify the chemistry of the surface, but also the morphology of the surface itself. The problem with the chemical treatments is that in most of the case, they involve the use of pollutant, chemicals, and also hazardous material. So we know that the world now is going in a different direction, and we are looking for more environmental safety procedures in order to achieve the same results. And one of the possible ways to do that is modifying the surface using different techniques which do not involve any chemicals treatment. And one of these is the laser pretreatment, which has been also demonstrated to be effective as chemical treatments in modifying both the surface topography and sometimes the chemistry of the material. In fact, for some metals, it's been demonstrated that also laser pretreatment can modify slightly the chemistry of the surface treated by the formation of oxides, which are mating the adhesive and are resulting in a strengthening of the joint. So the objectives of this work will be to study the effect of a pulsed laser ablation, which is a terbium-doped fiber laser, on a titanium alloy, which is one of the most commonly used for aerospace and biomedical applications. And doing this, we want to properly assess the relationship between the processing parameters that we are using on the laser and the surface modifications that we are inducing over the mating surface. And doing that, we can select a proper processing parameters in order to pretreat the substrate, to bond it together, and to verify if we can increase the strength of the bonding of the joint itself. So the first step is, of course, the laser pretreatment. As I reported in the slide, we cut out of a sheet which was 1.5 millimeter thick our samples by cold blanking, and then we cleaned the samples under ultrasonic bath in ethanol, and we treated the sample. In order to reduce the number of experiments and to focus into two different parameters that we could change over the laser, we fixed the power constant as 5 watt, and also the line spacing to 25 microns, which is also the spot diameters according to the lens that we were using. From the other side, we varied the scanning speed, so the speed at which the head of the laser was going through the surface, and the pulse fluence. And we changed them within 5 levels, so we had a total of 25 different tests. So the first analysis we performed was the analysis of surface morphology. So we did the SEM imaging, and on the upper part you can see the as received material, and on the other figure you will see the metrics of the treatment. So, as you can see, if we choose the pulse fluence of 10 joule over square centimeters, we don't see the effectiveness of the laser. Sometimes when we increase the scanning speed, we see like an effect of cleaning more than a really ablation of the surface. So we excluded these parameters to bond the samples, of course. From the other side, if we fix a scanning speed, like for example 650 millimeters per second, we can see that from 20 to 50 we are not able to realize the differences in the morphology within the different samples. And that's because the SEM itself alone cannot give us this information. So of course we had to go further and do further analysis. And because the final application is the adhesive bonding technology, of course, we need to verify if we could modify let's say, the chemistry of the surface and make it more hydrophilic, because that's what we want. So if the adhesive can, of course, penetrate better of the surface, so have a deep molecular interaction with the surface, we can have a more high quality joint, so a more resistant one. And the contact angle, as you can see from the figure, is going to decrease, so the surface is going to become more hydrophilic if we increase the scanning, if we decrease the scanning speed. As for the pulse fluence, we cannot see really a huge difference starting from 20 to 50. So from just these results, we can tell that once again, the speed has a higher influence on the changes than the pulse fluence. And these results were also confirmed by surface roughness measurement that we performed by a non-contact profilometer. And we measured basically the mean surface roughness. The baseline, so the as received, was around 2.4 microns. And as you can see, once again, as much as we reduce the scanning speed, we increase the roughness. So as for the contact angle that we saw before, we can say that it's maybe following, this kind of surface is maybe following the Wenzel regime of wetting. And once again, the pulse fluence seems not to affect so much the change also in surface roughness. Of course, we want to monitor both, because it's important to have not only a chemical interaction within the surface and the adhesive, but also a mechanical one. So of course, if we increase the roughness, we can improve the mechanical interlocking effect during the debonding process. In order to understand how deep was the surface treatment, so how effective was the laser treatment itself, we took a cross-section of our samples. We mounted it, cold mounted into resin, we polished, and we performed nano-indentation tests in order to verify if the hardness was changing along through the depth distance. And that's what's happening as well. So here I reported just a few tests that we performed, but of course we performed the test for the wall metric, and we verified once again that for the lower level of pulse fluence we didn't have a huge variation of hardness. It was more or less comparable with the as received. While for the other tests we had a harder surface that was going gradually to meet the hardness of the baseline material, so of the as received. We could say gradual, and I would say we selected these particular parameters because even if from the previous results we saw that the lowest scanning speed was giving the best results, we had a problem with this particular test. In fact, as you can see here, even if the hardness was really increasing on the surface, we had the formation of an oxide over the top surface, which was, according to, to our test, was not suitable for adhesive bonding. And that's because, first of all, as you can see, the drop of the hardness is very deep, very steep. So it means that most probably during the bonding process, this part of the material would be easily detached from the surface, or better, from the subsurface. And also, as you can see here, we had voids created by the process itself, because of course at the lowest speed and at the highest fluence we had a very rapid increase of the temperature of the surface, and the air was acting like a self-quenching. So basically the air bubble were trapped over the solidification stage, and this particular layer was, according to our ideas, a weak layer. So we didn't bond the sample for this case. In order to support this information, we also performed X-ray diffraction analysis, and basically what we could see was that the increase of the hardness could be attributed to the formation of alpha prime phase, which is a supersaturated macroscopic phase, which is harder than the baseline material. And also we verified a different peak for the test that I showed you before, so the lowest scanning speed and the highest pulse fluence, which confirms the formation of the oxide. So we decided to perform the test and to bond the samples using 350 millimeters per second and 1,250 millimeters per second, also because it would have been more appealing from a production rate instead of 50 millimeters per second. And we changed the two level of fluency. So we did 20 joule over square centimeters and 50. The bond line thickness was set equal to 0.2 millimeters, and we bond together the samples after the treatment, and we debond the samples acting with a pill load. And we did that because usually when you perform a TPL test, you are able to measure the absorbed energy, so the dissipation energy during the debonding process, which is important to understand if really the joint is has an improvement in its behavior. And we compared the results with the baseline, so the has received material, which was degreased before bonding. And the result, okay, here is not reported the as received, just because it was 50 times lower than the worst, yes, and than the worst laser-treated sample. So basically, we were able to increase the strength of the joint. And as you can see, once again, we confirmed the previous results, just saying that the pulse fluence had not a huge influence, but the process itself was driven by the scanning speed. Another thing that we could verify during the test was that the laser-treated samples had always a cohesive failure, so within the adhesive, while the as received itself showed a near interfacial failure. So of course this is another warning for us that seems to confirm that the laser treatment is improving the test. Here is not reported, but we also performed tests by sandblasting the materials, and we still had around half of the energy absorbed that the laser treated. So just concluding my speech, I just reported the experiments on titanium 6-4 treated by laser, and we applied the laser treatment to the final application of adhesive bonding. As a future work, we would like to study also the effect of different patterns over the surface, and if the crack propagation can be arrested with particular kind of textures. And also we want to see different configuration of joints, and also how the joints is responding to different environmental conditions like corrosion, high temperature, and also to test it under fatigue life. Thank you.